Welcome to this lecture number 4 of week 2 of the course on control systems. We started out this week by looking at some basic signal representation in control systems, how entire control architecture is some kind of flow of signals, could be from input till output, disturbance, noise, and so on and so forth. We also saw how things related to disturbance in the open loop versus the closed loop. And we also defined the notion of an impulse response of how does a system or what is a response of a system to certain inputs via the convolution operator. In the previous lecture, we talked about Laplace transforms. In this lecture, we will talk about inverse Laplace transforms and how the entire domain of Laplace transforms helps us understand or solve convolution better or even solve a simple ordinary differential equations. So the inverse Laplace transform, so I have a signal x of t, I do L of x of t to give me xs. So if I am able to move from the t domain to the s domain, I should be able to move back from the s domain to the t domain. So that is the notion of inverse Laplace transform, denoted by L inverse, will give me back the original signal in my time domain. Right? So this inverse Laplace transforms a function in the S domain back into the time domain. And mathematically, it is given by this expression here. Of course, we'll not go into examples of taking some functions in the S domain and calculating back, but we'll see how to use them. And all those beautiful properties that we had of the Laplace transform also translate to the inverse Laplace transform quite neatly. So this starts off with the property of linearity. Then we go to time shifting, time scaling, time reversal, multiplication of x. For example, we had if I had Laplace transform of x of t denoted as x of s, the Laplace transform of dx by dt was x s times x of s. Now, if I take a signal s times x of s, I do the inverse Laplace, I should be able to get back dx by dt. So that is what the multiplication by s does, right? And similarly, the division by s. So the Laplace transform of integral of x was 1 over s times x of s. So therefore, division by x should give me back the integral of the original time signal. Okay, this is nice. So one of the important concepts that we learned and spent a little time was about convolution in the time domain. What did it represent? Convolution in the time domain gave me, or it represented the amount of overlap of one function as it shifted over the other function. Mathematically, x convolved with h gave me this expression where I had to solve an integral of this form. Largely, this represents the output of a system h of t given x of t. So this was the convolution of x with h. If I call this as the output. Of course, this is a key relation that helps in determining the output of this system, of an LTS system. Given a certain input signal x of t, the output is y of t given an input signal x of t when the impulse response of the system is known. Okay, and then we were supposed to compute this integral here. What we will see now as a magic is that when the signals are transformed into the S domain, convolution becomes very easy. That convolution in the time domain just translates to multiplication in the frequency domain. As simple as I have x convolved with y, I take the Laplace transform. It just looks very nicely on the right hand side as the Laplace transform of x, which is the input signal, times the Laplace transform of y, which is another signal. So two signals convolved x and y will just give me output as x of s and y of s. If I were to write it equivalently here, y of s here would be x of s times h of s, if I may use that notation. Okay, how does this apply? So I just take a couple of quick examples of a convolution of x of t is t times ut. Again, ut is my unit step. U of t is a signal which has the value of 1 for t greater than 0 and 0 for t less than 0. Kind of says that these signals are active only for t is greater than 0. Now, what's the convolution of this of x with y? Okay, by the standard formula, I need to compute a not very simple looking integral term. Of course, this gets worse when I have exponential terms, cosine terms, uh, higher order terms, and so on. But I do a little trick. I take these two signals. What I know is that I apply the Laplace on x with y. It just turns out to be x of s times y of s. What is x of s? My signal is just x of t is t. And I know that Laplace transform of t is 1 over s square. Similarly, Laplace transform of sine of t is 1 over s square plus 1. Okay, so this is my x of s. This is my y of s. I can do little computations here to get the signals to get the signal in this form. Okay, once I do get it in this form, how does the signal look like in the time domain? I'm interested in how the overall convolution looks like in the time domain. I just do something simple. The uh, x star y will simply be the inverse of the inverse Laplace of xs or ys, or I'm just doing the inverse Laplace to get it back to the time domain. Now this is easier after I do this analysis here. Inverse of this, I have two functions here. So this must be a minus. Okay, I have two functions here. I just use a property of linearity. Inverse of sum of two Laplace transforms is the inverse of each of those individually. So I just apply that technique, and what I do is I'm just looking at the inverse of 1 over s square, which is t, minus inverse of 1 over s square plus 1, which is sine of t. A simplified process via the Laplace and the inverse Laplace transform. So start with the time domain, via the L, go to the S domain, do my analysis here, simplify the problem, do the inverse Laplace, and back to the time domain. That is the recipe that we will use in this context. I can also look at how do I solve ordinary differential equations. What we will see is that solving ODEs in the S domain is much simpler compared to solving ODEs in the time domain, because as we will see with this example, that ODEs become simple algebraic equations in the S domain. Suppose I have a differential equation of this form. Say I have d2x by dt squared, dx by dt x minus of x equal to 1. Let me assume that all the initial conditions are 0. So I do a Laplace on both sides. Okay, on the right hand side, I have the Laplace of 1, that will be 1 over s. On the left hand side, let me call the Laplace of the signal x of t as x of s. The Laplace of dx by dt, as we know, is just multiplication of x of s with s. Similarly, I do x square, this becomes s square. So this now simplifies to solving a linear equation with these 0 initial conditions, right? So I start with an ODE, differential equation. This is now just an algebraic equations. Which is easier to solve. And this Laplace transform is actually applicable to several kinds of signals. Signals could be continuous, could be piecewise continuous, periodic, step, impulse functions, and so on. And the properties of the Laplace transform of what we saw from linearity, differentiation, integration, time scaling makes the computations very easy. And not just that, inverse Laplace transforms also retain all of those properties. So I start again, the recipe would be start from the time domain, go to the Laplace domain, convert the ODE from the time domain to an algebraic equation. I do the analysis, and where the inverse Laplace again come back to the time domain. Okay, we'll see with the help of an example. So in an earlier lecture, we had this nice looking RL circuit where I just wrote down the Kirchhoff's law. So I had Ri plus L di by dt was equal to V0, leading to a solution of this form. Okay, so what do? I just do Laplace on both sides, giving me an expression that, okay, if Laplace of I denote as capital I of S, the Laplace of di by dt will be S times I of S, but the differentiation property. Okay, that leads to me to this equation here of the form R plus SL is I of S. And here I need to solve for I of S. I of S now takes this form. Again, what do? I'm in the S domain. I do all this nice analysis. Once it gets to a simplified form, I just apply the inverse Laplace in the whole of this signal. I use again the property of linearity. Okay, and then now I know, right? So the inverse Laplace of 1 of S is simply 1. Inverse Laplace of 1 over S minus A is e power minus at. Okay, this are both similar. And what we know or what we did here, the things are much simpler, right? I'm just solving a linear equation, sorry, an algebraic equation by just remembering some of those basic properties of Laplace transforms and basic Laplace transforms of some basic signals. Okay, let me do one more example of situations where I do not have do not have zero initial condition. So in this example, my I of 0 was equal to 0. Oh, so weird. So what happens when this is not 0? Okay, let us do this example. I have y double dot plus 2y dot minus 8y is 0 with some conditions for y of 0 and y dot of 0. I do the inverse, I do the Laplace on both sides. Double derivative becomes a s square, single derivative becomes a s. This remains as it is. And then I have the initial, so this is s square comes here, 2y dot, they come here, 8 times y comes here, plus those conditions on initial conditions of the double derivatives. So s y of 0 minus y dot of 0, here it will be minus y of 0 and x. So this again this just basic properties of Laplace transform. Properties of Laplace transform of d to x by dt square. Okay, now this is fine. I just recall the property. Now, how is y of s? Y of s is now simply 3s by 2s minus 8. Again, the same recipe. I start from t, I go to L, then here I do my analysis part. From the analysis, so this is equal to this one. This is my simplification process. Okay, now I just do the inverse Laplace and use all those linearity properties. Okay, what is the inverse Laplace of s minus 4? That is this signal. Inverse of s minus 2 is e power minus 2t. Okay, simple. So what did I do? I started off with a ODE with non-zero initial conditions. I applied the Laplace transform. My equation, which was a differential equation, turned out to be a nice algebraic equation. I just used some simplification methods to help me get back to the time domain via inverse Laplace transform of two simple signals. Okay, quick question. It's been a while since I asked you questions on the slides. What are the final value and initial value of this signal here, y of t? Also, y of s. Okay, so I'll just to just summarize. We had throughout this we had in this week's content, introduction to signals, convolution, Laplace and inverse Laplace transforms, and through that we learned how to simplify convolution, how to solve differential equations as simple algebraic equations. We will use all of this concept to now understand systems better and give them a little better notion of understanding, not just writing down differential equations, but as some nice looking input-output relationships which are easier to analyze. That will come via the concept of defining a transfer function. Later on, I'll define a few more properties of systems called stability. And slowly we will see how systems respond to different signals. We'll first start off with response of first order systems. That's coming up soon. Thanks for listening.